Hi, this is Math in 5 and I'm going to be doing the AP Physics 1 2026 FRQ question. Let's start with question 1. Okay, so water exits the nozzle of a fountain at an angle theta above the horizontal. Alright, so we have this like nozzle here and we have an initial velocity at t equals 0 so it reaches a maximum height h1. Okay, got it. So it's like we have a nozzle here and it's projectile motion. That's what I can deduce from it. Okay, now we got to sketch graph the horizontal velocity and the vertical velocity. Okay, for projectile motion, you know there's no acceleration, right? So the horizontal velocity v sorry vfx would be just equal to vot. There's no acceleration, so you have that initial velocity, right? You have that initial velocity and there's no acceleration, so the velocity graph would be constant and the slope would be 0 because there's no acceleration. So that means you'd probably do a constant line like this, a straight line, and then that's it. You have some initial velocity. Okay, but vertical velocity on the other hand, oh excuse me, it's yeah. Okay, so vertical velocity is represented by vy okay, so v final y equals vo voy times time plus 1/2 negative gt. Okay, so basically the projectile motion in the y direction is given by this formula, right? So what do we have here? We have constant acceleration, right? We know that, okay, so we know that this water, it goes up and it goes down. So you have a positive and negative velocity, right? And the slope, well, that's just gravity. And gravity equals negative 9.8 or negative 10. So we know it changes like meters or like, I mean, directions like halfway, right? So here, you'd probably like, with the same initial velocity, you'd, like, let's see, if you have like this is one, let's assume this is like 1/2 the time, it would be like this. Oh, my graph is kind of bad, but yeah, it's gonna be like something like this. Yeah, so that would be the vertical velocity. Number 2, derive an expression for the speed of the water exiting the nozzle. Express your final answer in terms of theta, h, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. Okay. Basically, since we know this is projectile motion and there's no time, there's only one kinematic formula that we could probably use to like derive. Okay, so that formula is going to be okay. Now with this formula, let's begin the derivation. So okay, it is given that basically we know the water's gonna the droplets are eventually have to come down, right? So therefore we know the final velocity is 0. So we can cancel this term out. Oh, remember, you gotta put this in. So the displacement in x. Okay, so since we have the acceleration, we're obviously gonna look for y. So before we do anything, just put it into the terms like this. So we have v final y squared equals voy squared plus 2 negative g h1. All right, let's get going. So we're trying to find the speed of the water exiting the nozzle. So that's going to be the speed of the water exiting the nozzle is going to be initial velocity. Okay. All right. So if we know this term is 0, let's do this. Okay, so we can put 2h1 to this side. Square root both sides. Okay, now here's the thing. When you're talking about initial velocity, we're not looking for the initial velocity of x or y. We're looking for the initial velocity of the whole thing. Well, how do you do that? Well, you know, initial velocity y is equal to initial velocity times sine theta. Okay, so basically, theta. Therefore, square root of 2j over sine theta equals initial velocity, or the speed of the nozzle. Sorry, speed of the water leaving the nozzle. Okay, put this into air terms. So 2gh1 sine theta, initial theta, so theta equals bo, and that's your final answer for number 2. All right. Part 3 asks, the nozzle has a circular cross section with the radius r initial. Derive an expression for the volume flow rate of the water exiting the nozzle. Express your final answer in terms of theta, height, and radius and physical constant. Okay. So this is a flow rate question. Interesting. So College Board. So this is like a mix of like kinematics and unit A. So interesting. Let's derive. All right. So this is a volumetric flow rate question. So okay. So we know volumetric flow rate is defined by the area times the velocity, right? This is going to be the equation for volumetric flow rate, okay? All right, so it's given that the nozzle has a circular cross section with radius r squared. So we know the area is going to be pi r squared. And the velocity, the initial velocity, you just put this here, you found it. Okay, do you have all the variables? Yeah. Express your final answer in terms of data. Okay, that's here. We have H1, we have R theta. Yeah, this is going to be the final answer. That's how you find volumetric flow rate. Just remember the continuity equation. I mean, you don't have to do it, but A1 B1 equals A2 B2. That's going to be like the volumetric flow rate of the whole thing. All right? It doesn't change. Okay, part B is asking. The fountain nozzle is replaced with a new nozzle with the radius smaller than R0. The water exits the new nozzle at the same angle theta above the horizontal. The volume flow rate of the water exiting the new nozzle is equal to the volume flow rate of the water exiting the original nozzle. Water exiting the new nozzle reaches a maximum height of 8. So we have to indicate whether 8 2 is greater than, less than, or equal to H1 by writing one of the following. Okay. So for this, we're giving it the radius is smaller than r theta. Okay, so we really know like the continuity equation: a1 v1 equals a2. Think about it. Okay, so basically, it's given that the volumetric flow rate is the same, right? So this has to be equal to each other. But if you reduce the radius, you reduce this, but therefore you have higher velocity, right? So once you have higher velocity, you're gonna have higher height. That's how it is. Because remember. Okay. So this. excuse me. H1 equals V of T over 1/2. So basically, the higher the initial velocity, so the higher the velocity, the higher the height. They have a positive correlation. That means, that means basically, since we're lowering the radius, H2 has to be greater than H1. Yeah, basically, yeah, that's question number one. Honestly, for this, yeah, you did type all of that out, but I'm not doing that. I'll just show you the logic, like you said. And also, I want to